Hello, and thank you for joining this promotion project presentation on a deployment plan for a meshed high voltage direct current grid. This webinar is a joint presentation between John Moore from TenneT, a transmission system owner and operator in Germany and the Netherlands, and myself, Hannah Evans from the CarbonTrust, a consultancy whose mission is to accelerate the move to a sustainable low-carbon future. John has led the development of the deployment plan as part of the promotion project, while I have contributed to the final deployment plan report and supported the development of the legal, regulatory and financial frameworks for meshed offshore grids. Today's presentation will provide an overview of the deployment plan and its key recommendations. We'll be covering a number of topics at quite a high level and would encourage you to listen to the other presentations in this series for more detail on a particular topic. In today's session, we will provide an introduction to promotion and the technical and non-technical steps required to deliver meshed grids. John will then touch on short-term projects which provide an opportunity to implement promotion recommendations in the short term, before concluding with an overview of the deployment plan. To begin, I'll set out the potential role for offshore wind in European energy systems. Offshore wind is central to decarbonising European countries. Currently, around 22 gigawatts has been deployed in European waters, and the European Union have stated that by 2050 we may need up to 450 gigawatts to fully decarbonise our economies and deliver climate neutrality. Of this, over 200 gigawatts may be deployed in the North and Irish Seas. Currently, most offshore wind farms are connected to the country in whose waters they are located by a radial HVDC transmission cable. As more offshore wind is deployed, this solution becomes more problematic because the distances to shore increase, which in turn increases transmission losses, particularly in AC assets. There's also congestion for onshore landing points as each wind farm has its own connection, and there becomes a mismatch between supply and demand, particularly for those countries with large wind resources but relatively low demand. Moving this energy to areas of demand will increase onshore congestion and reinforcement costs. To resolve these issues, several studies have indicated that an interconnected HVDC transmission grid is the most economic option. HVDC assets have lower transmission losses over longer distances than AC, and interconnecting transmission assets offshore will allow electricity to flow more directly to where it's needed, reducing onshore congestion and enabling Europe to make more effective use of its wind resource. So what is promotion and why do we need it? Promotion is an EU-funded research and development project on meshed offshore HVDC transmission grid technology. The reason for developing this technology is to enable the export of large-scale offshore wind and reinforce the internal market by interconnecting European states. As mentioned on the previous slide, several studies have indicated that to export the 200 plus gigawatts of wind envisaged to be realised by 2050 in the North Seas, an interconnected HVDC transmission grid is the most economic option. However, this requires a large shift from how offshore networks, including HVDC links, are built today. This picture shows all existing and planned HVDC links in Europe. These are all point-to-point links that either interconnect countries, export offshore wind energy, supply oil and gas platforms, or reinforce AC onshore grids. At some points, you can see that these different point-to-point links end up in the same physical location. However, the different colours of the lines indicate different rated voltages, which mean that these lines cannot be connected together in future to realise the benefits of an interconnected grid. On top of that, there are different converter technologies, different converter configurations, and a host of technical details that mean that these projects are not compatible. So what promotion set out to do is to understand what technology do we need, what regulatory and economic frameworks are necessary, and what aspects need to be coordinated or standardised to enable interconnected offshore HVDC grids to evolve. It's then sought to accelerate the development of those necessary technologies and develop recommendations for the necessary frameworks and standards to deliver a meshed network. So what progress has promotion made towards delivering meshed offshore HVDC grids? Well, firstly, we've been developing cost-effective and reliable control systems. Based on comprehensive simulation studies, we've developed functional requirements and generic specification lists for the control systems to ensure the stable operation of DC grids, offshore wind farms, and their interface to onshore AC grids. Methods to evaluate the compliance of real controllers with these requirements were also developed, and in addition, a method to analyse the harmonic stability of the control systems of different vendors were developed. On protection systems, functional requirements and generic specifications were developed for different protection systems. An open source hardware platform on which the various fault clearing strategies can be implemented was also developed. We've also sought to ensure interoperability between asset types by sharing recommendations for the development of standards and network codes. All aspects of HVDC grid deployment which require coordination for compatibility were collected and grouped based on the discipline and implementation level. These research results were consolidated and specifically disseminated to the relevant standardization bodies. We've also developed recommendations for the legal, regulatory, financial and economic frameworks for meshed HVDC grids. We've disseminated these findings to key policy, regulatory and industry stakeholders, including the North Seas Energy Corporation. We've also accelerated the development of HVDC circuit breakers and gas-insulated switchgear and demonstrated both of these at scale. Finally, we've produced a deployment plan for grid implementation out to 2050. This sets out the different grid designs, their relative merits, and the actions that need to be taken to ensure that there is an enabling regulatory framework for meshed grids and that the necessary technologies are ready to deliver at scale. The development of the deployment plan has incorporated 3 parallel streams of work. The first is a technical exercise where we assume that the non-technical environment can support a grid if we build one. This process has sought to understand the relative cost and benefits of different offshore grid development concepts. The second defines the legal and regulatory environment and other barriers that may need to be overcome before grids, rather than point-to-point structures, can be constructed. Finally, with the cooperation of promotion partners, we've looked at some real projects to identify opportunities to pilot some of the recommendations from the first 2 work streams in the wider technology development work carried out by promotion. I'll now hand over to John for the next part of the presentation, which focuses on the first work stream.
Thank you, Hannah. I will now summarize quickly the first sections. The wind scenarios have been built bottom-up within promotion. These have been validated against different NSOE scenarios. In discussion with our partners, each country has then been checked against what I can describe as national ambition. The latter has a political accent, and if we repeated the process today, the wind locations proposed may differ. There is continuous negotiation to rationalize and increase the size of permitted locations. For reference, our high scenario is similar to the forecast by the Wind Europe of around 200 gigawatts in the Northern Seas. What is important for our later analysis is that the wind locations and rollout are the same for all concepts. This is done to provide comparability in our analysis. However, if you are to build a larger hubs or a mesh or take a European perspective, you may adjust planning for a more specific and efficient rollout of wind. We defined 4 concepts to distinguish between wind scenarios. Firstly, we have business as usual, which consists of radial point-to-point connections from hubs to shore. Then we have a national meshed concept where constraints on point-to-point are relaxed, but hubs may only be connected to the country in whose EEZ the hub is located. Thirdly, we have a European meshed concept. Here, the constraints are further relaxed to allow connection to the closest onshore landing point. And lastly, we have an island or hub concept with much larger hubs in line with the North Sea Wind Power Hub model. The next slide gives the logic to this choice. In our modeling, we then looked at 5-year steps in the development of wind from 2020 to 2050. On each of the defined concepts, we've performed a 3-step optimization process, described in more detail in our companion presentations. What is more important to understand here is that the primary focus of our analysis was evacuation of wind energy to shore, and secondary focus was on international interconnection. Promotion does not look to solve specific onshore congestion issues. To give an idea of how the topologies can look, I've included this slide. It illustrates the different potential concepts in 2050 and can give a brief illustration of how complex some scenario or some concepts are compared to others. The concepts, as I explained, explore three dimensions. The first consists of bipole radio, or the bipole radial point-to-point connections for small 2 gigawatt hubs, and to an onshore connection point in the respective country. Interconnection is realized between countries. The first access is to allow multi-terminal and meshed grid structures to develop in order to optimize the cables required to evacuate energy. We then investigate the access of creating increasing cooperation between countries by releasing constraints on the landing on the shore. The last access we evaluate is between the 2 gigawatt hubs we define in the base case to large island hubs with up to 30 gigawatts of power distributed to different onshore connection points. Be aware, the work we have done is limited to these 4 concepts and 3 wind scenarios. As such, we are unable to make a full analysis, but can draw some preliminary conclusions which are intended to steer planning. In reality, full analysis would require more scenarios exploring more variables. However, this is not within the scope and time available within promotion. We also have a number of exclusions in our concepts that seem now unrealistic. We exclude offshore and large-scale onshore energy conversion or storage. We exclude the option to transport energy in DC directly to the consumption points, which may be further inland. And lastly, we do not consider distributed storage, which may also influence design. As stated, we have developed simplified models to assess the cost-benefit analysis. We employed a modified version of the ENSO-E approach for the CBA calculations, which is described in our deliverable D7.11. We used standard elements assigning costs based on capacity and specifications of the required connections. However, we realized that today building blocks are not yet standard, and over time technology may develop. Costing included best current estimates of equipment, and where that was not available, estimates based on component elements that are available. A learning curve model was applied to estimate potential for savings. This is tied into the volume of equipment delivered and used. Protection costs are currently a percentage of infrastructure cost. This is set at the high end of estimations based on analysis by the Supergrid Institute. The Supergrid Institute made studies on different grid elements resulting from our topology studies. Not surprisingly, they concluded that the best strategy and type of equipment was specific to each grid structure. They considered fully selective, non-selective, and partially selective solutions, utilizing fast circuit breakers and slower mechanical circuit breakers. Also, they concluded that the average cost of protection was between 2 and 9%. We created standard building blocks to define the different grid structures, hub structures and onshore structures, and to construct structures with interconnection. Size of the hub depends and is calculated based on the additional equipment needed for interconnection. Selecting a single HVDC level is required to mesh grids efficiently. We chose 525 kilovolts because it seems appropriate for the distance being covered. It is a compromise between today and the future. We realize that most existing projects are 320 kilovolts, and some new projects are considering this higher voltage. We standardized on 2 gigawatt maximum cables based on onshore load shedding constraints, and these were lower for the UK and Ireland and Denmark. However, if onshore constraints were relaxed, the size of the cable would need the size of the cable has a large impact on total infrastructure costs. Therefore, if we would go to 4 gigawatts, this could lead to up to 40% in capex savings. However, we would need to find some way to land that power. As stated, we've developed simplified models to assess the cost-benefit analysis. We created standard building blocks to define the different grid structures, like a Lego kit. We've had hub structures, onshore structures, and to construct structures with interconnection. We used standard elements, assigning costs based on capacity and specification of the required connections. However, we realized that today these building blocks are not yet standard, and as our costing exercise implies, over time, technology may develop. For selected required infrastructure, we used a simple decision tree. This allowed selection of the different components in construction of the grid. For the benefit side of the calculation, we used a separate generation, dispatch, optimization, simulation model, constructed to evaluate the quantitative social aspects of the different concepts and scenarios. A European node model is used in which each market area of the ENSO-E is represented by a single node. Each market area is therefore modeled congestion-free. We are aware that this may be a poor assumption, and clearly future research needs to consider a more detailed modeling of the onshore grid. The calculated social European benefits are the difference in the cumulated marginal generation costs from 2025 to 2050 between the business as usual base case and the three concepts. The results of the benefit analysis show social European benefits in all of the concepts when compared to the business as usual concept. Due to model constraints, we were unable to understand fully the impact of reduction of losses between the concepts. Qualitative benefits of the different concepts are also evaluated and compared. As in ENSO-E guidelines, we do not make a weighted conversion of the different cost elements. These are calculated or described in their original units. The result is a full cost-benefit report comparing the different concepts. The lowest overall discounted capital and investment cost is clearly for the island solution. Better optimization and potential future developments may improve this social benefit further. This is in spite of the higher anticipatory investment, which needs to be made early on in the prognosis. The 2 gigawatt N-1 onshore in-feed constraint results in many radial connections in all scenarios. A larger cable has a dramatic cost impact, as we can see in the diagram below. Meshing multi-terminal connections result in a lower cable length, but the overall costs of the system are similar, as protection and ancillary equipment costs are higher. Higher benefits are available to the meshed solutions. More efficient use of cables in the hub concepts leads to higher curtailment due to landing where energy must be transported onshore. In the EUR model, high cable utilization reduces interconnection possibilities. The conclusion is that the offshore topology planning cannot be done in isolation of the onshore grid. In our calculations and with current onshore constraints, the amount of curtailment for meshed concepts actually increases. We're still analyzing this, but our suspicion is that it is linked to the optimization, the shortest distance to shore, and to the interconnection between bidding zones and onshore not being optimized. However, the curtailment is also evident in other studies. It seems structural and is potentially a signal that we will need some form of storage or power to X. Absolute numbers may be misleading if we look at how much we predict it will cost. They could be plus or minus 30% of our estimates. Given increasing distance to shore, Promotion anticipates that for full evacuation of wind, transmission investment will be approximately 1 billion euros per gigawatt. For the high scenario, a total of around 200 billion euros. This is, of course, dependent on the concept, albeit the cost per concept indicate limited variation. This is in line with published current estimations for offshore transmission by the OFFTOs, but does not reflect a measurable decline over today's costs. This may be due to increased distance to shore. However, over the promotion forecast period, costs do indicate a decline from 1.2 to 1.3 euros per billion euros per gigawatt in 2025 to around 0.8 to 1 billion per gigawatt in 2050. This large investment for the total grid is almost a doubling of current rates of investment for an extended period. This may place pressure on the current funding models of grid building. So, in conclusion, what we did see was that quite complex structures are proposed by the optimizer. In both the national and the European concepts, multi-terminal and mesh structures appear early. The optimizer looks 2 periods or 10 years ahead. Meshing requires forward planning in all the steps to include the anticipatory investments. The hub concept is in all cases connected to multiple landing points and therefore can be seen as meshed. Building hubs has an upfront cost, cash out of the door early. The hub solution is cheaper in our models and the only one which may be materially cheaper, but this anticipatory aspect has to be considered. Remember, in our models, we have not optimized the wind rollout around the major hubs. We also did not fully optimize the location of the hubs. These are manually located in areas where the visual density of wind generation is located. It will also reduce the number and character of offshore cabling. European meshing made cable utilization higher, leaving less capacity for interconnection. The nearest connection point to shore is not always the best one. More complex hub constructions and increased meshing over the national concept, which still had more radial connections, leads to more complex hub structures that compensate for less cable. Manual increase in interconnectors between close-by hubs does not pass the financial cost-benefit analysis. And lastly, business as usual or radial connections are still very evident in all generated concepts. The technical configuration of a bipole with fixed return, which we used, may be part of the reasoning, as this has an inherent redundancy. With that, I'll pass over to Hannah.
Many thanks, John. I'll now talk through some of the economic, financial, legal, regulatory and market recommendations we have made in promotion. As mentioned earlier, we'll be covering topics at a high level, and I would encourage you to listen to the other presentations in this series for more detail. This first slide focuses on how we can assess the added value of projects within a meshed grid and how these should be paid for by European countries. Firstly, cost-benefit analysis is a well-established tool to guide investment decisions in various sectors, including the energy sector. The most well-known CBA methodology is in an EU electricity context is the one for energy infrastructure published by ENTSO-E. A harmonised system-wide CBA methodology is applied by ENTSO-E to provide objective, comparable information about the projects included in their 10-year network development plan. The CBA methodology is also relevant for establishing a regional list of projects of common interest, or PCIs, as evidence for national regulatory authorities and the European Union to decide on whether to grant a project financial incentives or assistance. After reviewing the methodology and case studies of its application in several projects, the promotion team identified aspects of the CBA methodology which should be adjusted to enable proper consideration of meshed as opposed to point-to-point projects. Firstly, to increase transparency of the CBAs of PCIs, regional groups could express their policy priorities via the PCI eligibility criteria. This could act as an early screening step prior to a full monetised CBA. Secondly, interactions between offshore PCIs should be taken into consideration in CBAs. Projects with potential synergies should be considered in clusters rather than in isolation. Finally, there should be full transparency over the costs, assumptions and methodologies used. Results from the CBA are also valuable in the process of making cross-border cost allocation or CBCA decisions. CBCA determines how much each country who benefits from a project should contribute towards its cost. Historically, these are agreements between two countries, but for meshed grid assets, they could involve multiple states. The amount each party should contribute will depend on the direction of flow of electricity and should be calculated based on the extent to which the connected countries benefit from using the asset. As with CBA, there should be a coordination of CBCA decisions for complementary projects. This could be achieved by taking a clustered approach in which a CBCA agreement is reached for a group of projects. In addition, promotion recommends that complete CBCA decisions are carried out. That is, a CBCA which considers how costs would be allocated between nation states, both with and without a contribution from the EU's Connecting Europe facility. This is necessary as CBCAs are often carried out prior to a decision on whether CEF funding will be provided to a project, and having to revisit a decision in light of such funding being declined can result in project delays. Moving on to financing structures, the overarching objective here is to provide clarity and certainty to investors so that they understand the risks and rewards of investing in offshore assets and structure their investment accordingly. As such, a financial framework for a meshed offshore grid will only succeed when an adequate legal and regulatory framework is in place. This should provide clarity on ownership structures, revenue mechanisms and incentives. It should also include a liability regime between the offshore transmission asset owner and the wind farm. In the short term, these liabilities may be agreed contractually between offshore wind developers and those responsible for constructing transmission assets. However, longer term, as the grid becomes more interconnected, a liability regime should be part of the regulatory framework. On a slightly different note, the promotion project recommends that national regulatory authorities fund appropriate anticipatory investments in transmission infrastructure. The decision to allow an anticipatory investment must weigh up the potential cost saving of the anticipatory investment compared to the cost of incremental expansions, with the likelihood that the anticipatory investment will be utilised. Several aspects of building a meshed offshore grid may require an anticipatory investment, from building an initially oversized platform or transmission cable to investing in an artificial hub to accommodate future offshore wind deployments. Transmission owners will only invest in assets in which they know they will receive a commensurate return and remuneration for. The rate of remuneration and return on investment should balance the obligation to provide cost-effective networks for consumers with the need to make those transmission assets a viable investment. Finally, diverse financing structures and financial instruments should be used to enable new sources of finance to be able to invest in transmission assets. As John mentioned earlier, building a meshed offshore grid has been estimated to cost up to €200 billion by 2050, depending on the grid design and configuration chosen. Alternative structures such as special purpose vehicles or SPVs for individual transmission projects could allow new investors into the market or allow additional finance to be raised while reducing the risks to the parent company. The OFFSHORE regime in the UK is one example of how transmission networks can be opened up to new investors. Also in Germany, TenneT incorporates SPVs by forming equity partnerships for individual connection projects. Alternatively, financial instruments such as green bonds with low interest rates and long maturities could be a successful form of corporate fundraising for offshore transmission assets with an environmental added value. Moving on to look at the legal and regulatory recommendations. The main recommendation is that the backbone of a common legal framework should be a North Sea agreement in the form of a mixed partial agreement. A mixed partial agreement is an international law agreement between North Sea coastal states and the EU. It can be signed by individual states both within and outside the EU, as well as by the EU itself, making it compatible with the fact that the UK has left the European Union. There is a precedent for these types of agreements, including the Rhine Convention and the Alpine Convention, both of which sought to lay out environmental protections for those areas. The purpose of a North Sea agreement would be to set out a common interpretation of the law of the sea, including a common definition of offshore hybrid assets and the extent of jurisdiction states have over these assets. It would set out the governance of a meshed offshore grid, enable regulatory cooperation, provide a process for conflict resolution, and also a process for amendments to allow the agreement to be built upon over time. Looking in more detail at offshore hybrid assets, these are transmission assets which are both interconnectors between countries and also evacuate power from offshore wind farms to shore. Under current market models, a definition of hybrid assets is necessary to distinguish them from point-to-point wind farm transmission cables and interconnectors, each of which is regulated separately and in a slightly different way. A definition of hybrid assets has been included in the recital of the recent EU electricity regulation, but promotion recommends strengthening this definition by adopting it in the operative part of the regulation, and that the legislation should specify the legal and regulatory framework for offshore hybrid assets in more detail. This framework could then be tested on a pilot project and refined over time. However, the extent to which this definition is required in the long term is dependent on future market structures, which I'll touch on later. However, promotion recommends progressing with both the offshore hybrid asset definition as well as potential changes to market structures to keep options open over the short to medium term. On another topic, as we move to more multi-jurisdictional projects, the complexity of dealing with multiple planning departments increases the risk of planning rules delaying or preventing projects. However, promotion research doesn't advocate aligning across all planning regimes across European countries, as this is a disproportionate step and could potentially stifle innovation. Equally, there are unique environmental conditions which need to be taken into consideration in each country. However, there are some risks which we think could be mitigated through consistency of approach and cooperation between countries. So these include adhering to the principle that once granted, a permit or license will remain valid for the duration of the construction and operation phase to reduce the risk to the offshore wind farm or transmission asset owner. Decoupling the offshore permitting process from the cable permitting process, but ensuring that the project commissioning dates are coordinated. Simplifying the permitting process by creating a one-stop shop for key project permits. And this could apply to both a single country or a multi-jurisdictional project, and could also apply to both offshore wind farms and grid development projects. We recommend a move towards joint environmental impact assessments, or EIAs, for cross-border projects, because the criteria for these EIAs and mitigation measures can differ per country, and EIAs at the moment have to be made on a national level. So this can mean that cross-border projects have to require 2 or more EIAs, which could result in different mitigation actions for the project developer depending on which part of the project sits in which jurisdiction. This can add time and cost to the permitting process and the implementation of those ongoing mitigation measures. And finally, allowing for technology agnostic planning. So the development and planning process for offshore transmission assets can take a number of years, over which time technologies develop. By including some flexibility within planning permits to allow for these developments, projects can deliver the most cost-effective solution available at the point the design is finalised, not at the point the planning permission is first applied for. Moving on to decommissioning, so at the other end of the project lifetime, more research on the impact of different decommissioning approaches should be carried out, and guidance on decommissioning of offshore wind farm and transmission assets should be developed at an international level by IMO or OFFSHORE. Finally, looking at regulation, promotion recommends that the grid should be regulated through the cooperation of national regulatory authorities. This aligns well with the additional powers granted to ACER in last year's Clean Energy Package. Whereas ACER's role was previously limited to coordinating and advising on activities between national regulatory authorities, it now has additional powers to supervise the ENSOs for electricity and gas, the regional coordination centres, and to assist national regulatory authorities in performing their tasks. ACER will also be involved in the development of network codes, guidelines and methodologies, and in monitoring their implementation. Moving on to look at government. Government will have a really important role in enabling the implementation of several recommendations in the promotion project. Central to this is ensuring there is a clear policy direction for the national deployment of offshore wind, and that this national ambition aligns with wider European goals. This will enable the effective use of wind resources across the Northern Irish Seas. To deliver the necessary rate of deployment of offshore wind, government industrial policy can support investment in supply chain infrastructure such as port facilities and local manufacturing facilities. In addition, provisions of innovation funding for the demonstration of new technologies in the marine environment can help drive cost reductions and the commercialisation of new offshore wind technologies such as floating platforms. Finally, government can invest in training to ensure countries have the right number of skilled personnel for offshore projects. To give a couple of examples, the East of England Offshore Skills Centre in the UK offers grant-funded courses to train new offshore wind technicians, and this centre is co-located with an existing college and was a collaboration between the main local offshore wind employer and local councils, the local enterprise partnership, and the Education and Skills Funding Agency. Another example is the National HVDC Centre in Scotland, which was funded by Ofgem, the UK energy regulator. And this was following a competition for new innovation ideas. What the centre includes is a state-of-the-art simulation equipment for HVDC networks, and is also a training facility for new engineers. Its facilities have actually been used to test some of the protection systems developed in the promotion project. Finally, we come on to market structures. Currently, offshore pricing zones for electricity are an extension of onshore pricing zones, and wind farms have to bid into the bidding zone for the country in whose waters they are located, and generally to which they are connected. As a meshed grid develops, wind farms will be connected to more than one bidding zone, and electricity will flow to the bidding zone with the highest price. Therefore, it's not a given that the best choice is to pay a wind farm the electricity market price of the country in whose EEZ they are located. Promotion looked at two alternative arrangements, a single offshore bidding zone for the North Seas and a small zones bidding model, where each wind farm or small group of wind farms have their own bidding zone. Small bidding zones are economically efficient for both wind generation and offshore storage or hydrogen production, however may lead to lower offshore wind revenues due to congestion. Therefore, some form of revenue support or stabilisation will still be necessary. How this is funded should be established as part of a joint support scheme for offshore wind farms between North Seas countries, with contributions made based on the beneficiary pays principle. Further details on the small bidding zones model is available in the presentation on market models. I'll now hand back to John to discuss short-term projects.
Thank you, Hannah. Quite early on in the project, it was learned, or at least we realized, that we could not construct a full-size demonstrator for some of the equipment we wanted to demonstrate. And it's clearly almost impossible to finance using a subsidy or grant a full-size demonstrator. So what we did within promotion, we reviewed existing HVDC links and the ENSOE TYNDP for 2018 for future HVDC links. And what we tried to do was identify potential locations where we could implement the HVDC and meshing equipment that we required to test that equipment in a real-life situation. Promotion, of course, can only really develop equipment in the lab or to a kind of theoretical level. So to go to the next level, we needed to test the equipment. The owners of 3 projects agreed that we could use, or that we could support them in pre-feasibility studies. And we've made per opportunity, we've made different levels of studies. We've been in depth in some, we've been in others, have less depth. The focus has changed between the different studies. However, on 3 opportunities, we have done some quite extensive work to evaluate those and prepare them if the company would like to apply HVDC equipment. The results of these, the technical results will be made available publicly. However, the conclusions and some of the more politically charged results will remain confidential only to consortium members and to the EU. If you do need more information on these projects, or if you do want to see more information on these projects, you can ask the project owners, and they may give you access to more information. In today's presentation, we have just scratched the surface in terms of the volume of work done and the conclusions we can draw. There's more depth available in the other presentations within this series, and there's even more depth if you dive into the deliverables that which are on the web. Promotion, while fundamentally advancing HVDC meshing technology, has achieved much more. We have considered the cost benefits of different analysis of different topologies versus radial connections. This does support the consideration of multi-terminal and mesh grid solutions and does favor large hubs in order to reduce costs. We have considered the conundrum of legal and regulatory questions, whether to create hybrid assets or whether to adopt early on a small bidding zone model. We have looked at ways to kickstart the process by which an HVDC grid may be tested in our review of the short-term projects. In our deployment plan, we identify what extra will or may be required to progress a meshed offshore grid. The documents generated are quite deep and specific. They may be used as reference. If there is an area you are specifically interested in, please contact us. In terms of our outputs, what the deployment plan does, it doesn't say you must do this, you must do that. It provides direction and the actions that are required to progress the next step in building offshore grids. In terms of technology, anticipatory investments already need to be done early on in the period due to later investments far offshore, where offshore wind farms will be connected to those close to shore. Sort of interoperability ties into the anticipatory investments where we need to have as soon as possible rules on the interoperability of components from different manufacturers to work with each other. If you extend a grid, you need to be able to connect that to something, and if the two manufacturers don't work together, then the whole system doesn't work. Also, manufacturers will tell you you can connect everything in one way or another, but if there are no rules on interoperability, that will always increase cost. The island solution, with its long lead time, needs development early to be able to build that sort of the connection that's required from 2030 to 2035 onwards. Island solutions save money and should be considered, but that early planning is essential. DC circuit breakers must be tested in industrial and real-life settings in order to prepare for their applicability in 2040. GIS can save a significant amount of space on platforms and therefore needs early development. GIS currently uses SF6 gases, and research needs to be undertaken to start using other gases and with a lower greenhouse potential. At the moment, GIS is only necessary when meshing, but if it is also usable in a normal point-to-point DC connections, it may have to be moved up in timing. So with that, I would like to close this presentation. If you have further questions, don't hesitate to contact either myself or Hannah. But actually, more importantly, it's time to go out and build the grid. Thank you.